Okay, so this next lesson can take a little bit to get your head around, and it's called trigonometry in 3 dimensions. So although right-angle triangles are 2-dimensional shapes, those shapes can be used to solve problems in 3 dimensions, which only really makes sense if you think about it. When we're in construction or woodwork or something like that, we use a right angle, like a set square, to make a straight cut, those sorts of things. So obviously right angles have purposes in 3-dimensional areas, but it can take just a little bit of getting your head around to just make sure we understand what it is we're looking for. So I'm currently teaching from B1, I think it's B1. Anyway, I've taken a photo of the corner of the room. Now, of course, buildings have to be square. That's kind of a really important part of buildings. So this angle in here needs to be a right angle. That's where the floor joins the walls. That needs to be at a right angle. But as well as that, this I'll do it in a different colour. This angle here, where the wall is, that also needs to be a right angle. The wall needs to go up at right angles to the ground. And by the same token, this angle in here needs to be a right angle as well. So what we've got is sort of 3 right angles all meeting at a point, which kind of makes sense if you make with your hands, make some right angles with your hands and then place it on a desk, you should get that same sort of situation. So just understanding what to do with that in a practical context can take a little bit to get your head around, but it's not something that should be too foreign. We have, in just about, you go to the corner of just about every room, you're going to see the floor meet at right angles with the wall, and we're going to see the 2 walls meet at right angles to each other as well. Okay, so going here with example 1, from point X, which is 25 metres due south of the base of a tower, the angle of elevation is 47 degrees, and point Y is 15 metres due east, which means that point X and point Y are right angles to each other, because south is at right angles to east. All right, as well as that, the tower is at right angles to the ground. So it's very similar to this situation we've got over here. If we think about it this way, here's our south. That's a bit hard to see on there. I'll go with the blue. So sort of here's our south, here's our east, and here's our tower. So it's sort of a very similar situation. We've got 3 90-degree angles because the tower is at 90 degrees to the ground and south's at 90 degrees to east. Okay, so we want to find the height of the tower to 1 decimal place. So if I look at these 2 triangles, the triangle here on the left-hand side I think will be the better place to start because I know an angle and I know a distance. All right, whereas in the other triangle I don't know the angle. So I'll start my solution by saying in triangle XOT, right, we've got a distance that is adjacent, and we've got a distance that's opposite our angle. So we've got a situation where we might use tan, opposite over adjacent. So tan theta equals the opposite over the adjacent. Now in this case, the angle is given, that's 47 degrees. And the opposite side I don't know, that's just h. And the adjacent I do know, that's 25. So we end up with h equals 25 tan 41 degrees. And we'll give our answer then. We'll use our calculator. So 25 times tan 41 degrees, close our brackets. So to 1 decimal place, that's going to be 21.7 metres. Okay, now that that's done, we want the angle of elevation of the tower from point Y. So now we're looking in this triangle here. We've got the yellow triangle. All right, so we already know the height of the tower because we just worked it out. And now with the height of the tower and this angle along here, this distance along here, the 15 metre distance along here, I should be able to work out that angle. So for this one, I'm using that yellow triangle. So I'll say in triangle, what is that one, YOT. Now if we think about this and we've got our angle, I know this side, that's my adjacent side. And then I also know my opposite side. So I'll once again be using tan. So tan theta equals the opposite over the adjacent. The difference here is this time I don't actually know the angle. But what I do know is the opposite side, that's 21.7. We just worked it out. And the adjacent side is 15. So therefore theta is going to equal tan to the minus 1 of 21.7 over 15. And we bump that into our calculator. Now there's two ways you could go about this. Because I've got 21.7 there, I could, and I think I'll do this, I want the most exact answer I can give. So if I go shift 10, and then I put my answer, because that way it won't be to one decimal place, it's the full answer we had last time, over 15. And that'll give me a much more exact answer. So there's our angle elevation. I'm going to do that to the nearest minute in this case, so 55 degrees, 23 minutes. And there's our angle of elevation. We might just say something like, therefore angle of elevation equals 55 degrees, 23 minutes. Okay, so moving right along, there's just the two examples here today. So example 2, two straight paths up to the top of the cliff are inclined at angles of 22 degrees and 25 degrees and 22 degrees to the horizontal. So here's our two paths. If path 1 is 114 metres long, let's just write that on there, so that's 114 along there. Find the height of the cliff to the nearest metre. So what I've essentially got there is a right angle triangle here, because that is going to meet the cliff at right angles. And what I want to know is the height here. Okay, so the triangle I'm using is actually sort of this triangle here. It's kind of hard to see, but that's a right angle triangle in there, because this path, the cliff hits the ground at 90 degrees, and the angle this path makes creates a right angle triangle. So we're going to, if we look at that particular example, we've got I might just, I'll make a few, so we're clear where you're dealing with that one. So this is question A, we're going to be dealing with that triangle. So we've got an opposite side to the angle, and we've got a hypotenuse. So we're going to have sine theta equals the opposite over the hypotenuse. In this case, the degree, it's 25 degrees. The opposite side we don't know, that's the height of the cliff, but the hypotenuse we do know, that's 114 metres, because it's a 114 metre long path up to the cliff. Okay, so if we work out that, we're going to end up with h equals 114 sine 25 degrees. Well, that's a very big degree sign. And so we'll plug that into our calculator. So 114 times by sine 25 degrees. And that's going to give us 48 to the nearest metre, it said, so 48 metres long. Okay, now if the cliff, in this particular example, we're allowed to assume that the cliff is the same height. So this is going to be the same, so we've got the same height. So now we're going to be dealing with this triangle in here, because what we want to know is the length of this path. But the height of the cliff doesn't change, so we already know the height. So we've got, in this case, an opposite side. Oops, sorry, I'm using the wrong pen, that's why it's not working. We've got an opposite side, and we've got a hypotenuse. So in this particular instance in B, we've got, if we're using the opposite of the hypotenuse, we're still using sine. So sine theta is the opposite over the hypotenuse. But in this case, we know it's 22 degrees. and the opposite side is the height, which is 48 metres, and the hypotenuse is the bit we want to know, that's the path. So I'm going to call that, I'm just going to say path 2. All right, so once again, this is one of those situations where we can flip the bottom around, and so we're going to end up with path 2 equals 48 over sine 22, and so we put that into our calculator. Now in this case, once again, I think I'll just use that number that I've got there in my calculator, so rather than just put 48 in and give a less exact answer, I'll use the answer I had before, and that's over sine 22. And we press equals and we end up with 128.6 metres. Okay, so it's just important to understand that when we do things in 3 dimensions, sometimes our triangles don't look right angled. So we've just got to look at the circumstances of the question and see if what we've actually got going on here is a right angled triangle, because in both these cases, the yellow and the blue triangle, they don't really look like they're 90 degree or they're like they're right angled triangles, but when you actually think about it, they have to be. And so that's the end of today's lesson. Have a go at those.